Okay, so I hope I'm audible. Mm, Welcome you all to another doubt clearing or problem solving session. So this is week 9, and I'm Swastik Sharma. This is a doubt clearing session for the course Smart Grids, Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena from IIT Roorkee. I'm Swastik. I'm a PhD student at IIT Kanpur. So in the whole course, we were discussing some of the technologies that are being implemented for the smart grids and how these technologies, these control functions, or other technologies that are used for implementing interoperability or increasing the usage of DRs at the distribution side or um, the microgrids, etc., etc. All of them now have culminated for us to demonstrate whether or not what we propose is true or not, right? So we can't just propose a theory and be like, okay, if it makes sense, it makes sense. We have to have it make sense, right? So this week, the whole week, we focused on demonstration of few particular examples. In this doubt clearing session, unfortunately, it's not convenient or it's not it's impossible for me to do a demonstration offline. But yeah, we will be touching all of the concepts covered, and I will be taking your doubts, and we'll be going through some MCQs as well that will help you solve the next assignment. So yeah, let me share my screen. Okay, so my screen is visible. Okay. Okay, so before we move on to demonstration, so some of you who may have gone through the lectures, they would have noticed terms like controller, hardware in loop, or power hardware in loop being used by the instructor, right? But I would first like to give you a brief overview of what these terms generally mean. So for this, I've taken the slide deck of Dr. Shreyasi Som. She was my senior at IIT Kanpur. She has gotten her PhD now, and in this she gave us a brief overview of her work, and she taught us what controller hardware in loop is and what kind of validation do we expect from these real time simulations, right? So you must have heard this term real time simulation. So what is this real time simulation and why is it important? So first of all, when we create a circuitry on let's say MATLAB, you must have seen that the seconds that it says, it's not something that is so it could move very slowly or it could move very fast, right? The seconds are not synced with the clock that we have on our desk, right? Now, usually those kind of simulations are used to simulate the design part of the system, right? So if you propose something novel, you just simulate to show, okay, yes, your converter, what you proposed for is making sense, or uh, the 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 relays that you want to showcase, they are really working or not. But in real time, they have to be synced with real time, right? We can't say that a relay which is operating 1 millisecond in our control in our software, it's not even operating in 5 seconds that we wanted to do, right? So it would be bad for our system. We want to have the the we want to validate that what we are proposing would work in real time. Even a seconds lag, even milliseconds lag would be disastrous for our system, right? And that's what we have, these real-time digital simulators. So we have Opal RT, it's a company, and then we have RTDS, we have Typhoon Hill. All of these are real-time simulators, and what they do is they are basically one very costly. So they are their one rack could cost, I mean, up to a crores or something, right? So IIT Kanpur is the only institution in India that has all three kinds of simulators, digital simulators. We have Opal RT, we have Typhoon Hill, and we have RTDS as well. And this simulator is something that we use. I mean, I don't use it for my research, but this is something that people use, which is beneficial for what they are validating, to validate that it will work in real life as well, in real time. So that's what uh, these hardware components, RTDS, Opal RT, or Typhoon Hill, are used for. So what are we trying to validate? So firstly, it's like so what are we trying to validate? Let's say we proposed a logic. We proposed a controller. Let's say we propose that our buck converter, which has two switches, synchronous buck converter I'm talking about, which has two switches, it should switch in this way so that our algorithm could make sense, right? Switches, we are controlling it using the PWM pulses we are generating. So in order to make sure that in real scenario it's going to make sense, in real time it's going to make sense, we validate on these platforms, and it's a must for them to pass this validation to be able to call a reliable algorithm once and for all. And this makes our product acceptable, reliable, and ready for deployment. So what is one thing we need is we do validation, and after that we do field deployment. Let's say we proposed a relay to work in certain way, we validate it, and then we need to deploy it in field, right? And in field it should work like we want it to. Otherwise, if it's not working in real time, what it's a pass, right? And how to validate it is using these platforms on. So this platform, the demonstrations that happened in this week, they were all conducted on Opal RT, but they can be conducted in Opal RT as well as RTDs. So let's talk about what kind of validation is. So firstly, when we propose a control logic or a protection logic, let's say a control logic is for converters, and protection logic is for relays or other protection equipments, right? So first of all, we do software in loop validation. So in RTS, we have RTDS, we have in RTDS we have RSCAD. So it's like MATLAB for RTDS and for real-time simulation. We first implement our circuit in this platform. So all of our control or protection logic, it's everything is in the software. Starting from our controller protection logic, our converter or relay. Control is for, we do firing pulses for converter, and we do trip signals for relays, right? So I'm showing for both protection as well as control of converters. And it's connected to the rest of the network to a bus on the line. So this is software in loop validation. It will in real time. So this RTDS, its clock is synced with GPS, Global Positioning Satellite, and this helps us validate that whatever the so let's say our control logic proposes, we have to fire the pulses at every 1 millisecond, right? So this 1 millisecond should be validated or simulated in real time. That is, this 1 millisecond should mean 1 millisecond of what we say. A 1 millisecond of MATLAB could be 5 seconds as well. I mean, if your computers are slow, you must have seen that whenever you simulate on Simulink, it usually takes time. In the bar down below, you see that a number ticking, 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 but it takes time if your PCs are slow. So what it is that it does is it proposes that in real time how your software is behaving. It tells you everything. Now, so this was software in loop validation. So you did your software in loop validation. Your software is working perfectly fine in real time. So what you do, you remove your controller. Once you remove your control logic or protection logic, now it becomes a controller hardware in loop. So this control or protection logic, which is implemented on a digital signal processing board, a DSP board, it's implemented outside of the software. Now your RTDS is in direct communication with your DSP board, which is simulating the rest of the network inside of that RSCAD platform. So rest everything, your converters in the rest of your network is still inside the circuit, it's inside the software, which is in real-time simulation, but your device under test or the logic that you are proposing under test, you remove it outside of the software. So first you did your software validation and then you removed it outside of your software and it's in a separate logic board. We'll discuss how we do that if time permits. So let's say your controller hardware in loop makes sense. Okay, you validated it. It's behaving as expected. Now what you want to do is you would want to remove your power hardware as well. What is your power hardware? Your converter or your relay. Okay, my DSP board is issuing signals at the perfect time instant that I want to. But is my converter behaving in as expected in real time? Is my relay behaving as predicted? As is it tripping in real time? So what we do is we remove our hardware as well. Now it becomes a PHIL, also known as power hardware in loop. So all of your device under test, you remove it outside your platform. Rest of your network, since you don't have the access to the network yet, so you can simulate your network inside that RSCAD platform only, but your hardware is moved outside of that software. So what you're left with is PHIL. Okay, you validated it. Now your control logic, protection logic, your converter or your relay is working perfectly fine. It's working as expected in real time as well. Now what's next? Can anyone tell me what's next? Is there any kind of validation we would want? So we did our power hardware in loop. We started with our software. We removed controller. Then we removed our converter. What are we left with is our network, right? So the last step is field validation. Let's say you have a microgrid. You can use your microgrid in conjunction with your device and test if it's working as expected in field or not. So reaching this field validation stage takes a lot of time. You you generally have heard of this. What is it called? Forgot its name. It's technology readiness level. It's TRL. This is a metric used to test at what stage your technology is. Usually, this field validation takes a lot of time to come to. It's 10 years at most. So people working at a very advanced stage only move to that field validation stage. Our PhD work ends maybe here or here. It doesn't go beyond that because it's difficult for us to move beyond it because it takes a lot of time. So this is what we will do. So you have four steps of validation. First, you do software in loop validation. Then you do controller hardware in loop validation. You move on to power hardware in loop validation, and the rest left is your field validation. In the demonstration of this week's lecture, we have done. I have not done it. The instructor has shown only the controller hardware in loop validation of all the components. So so I use the word RTDS, right? So an RTDS is nothing but it provides real-time measurements. So it tells us if how our device is working in real time, which is synced with the global positioning system clock. So this tells us time up to the I mean this milliseconds range. It's used to it's connected with a satellite and it's a very costly system. It costs around 20 to 25 crores. And it's required for us as power engineers to validate our systems before we propose anything because making it make sense in the software is not enough for us. We have to make it make sense in the at least in the power hardware and loop validation. So it has a synchronization card, it has an interface card. So I won't be going into details, and it has a digital input and output card and analog input and output card, which is in connection with your RSCAD, where your simulation of the rest of the network happens. Your DSP is used to fire pulses or control signals, usually to your setup, most probably a relay or a converter. you use it to, simulate your system. So we won't go into much of the detail. I just wanted to give you a fair, quick overview of how different kinds of validation is done, and what we have done in this week's lectures. So, yes, so this week we have done demonstrations only. So we build it. So we started with a very niche area. We started in week one with the discussion of everything in brief. And then we started building upon all of the smart grid technologies that are being implemented in the world right now. And now, from this week onwards, we have moved on to the demonstration part of all of our uh, technologies. So, yes. So we started with the demonstration of a solar inverter. So the demonstration was done basically for a single stage solar inverter only. But there are two kinds of solar inverter. One is a single stage where you have a direct inversion, but there is a dual stage converter as well, where uh, it is a DC link, uh, front end and back end converter, where the back end converter, which is a DC-DC converter, is usually a boost converter and connected across a DC link, then an inverter stage. So this offers better control because of the fact that we can um, uh, boost up our output voltage from the PV panel. So basically, what we want is the solar panel gives us DC output, and since we want to synchronize it with our grid, we want it to be AC power because we use AC. So, and the solar inverter needs to be able to provide us high fidelity currents, that is usually high quality currents. So, the THD, the total harmonic distortion of these currents should be minimum, which is usually industry standard is less than 5%. And uh, we use the solar inverter to provide grid support as well in the form of reactive power management. Now, a single stage converter, since it has only one conversion state, the conversion losses are very less. So the converters that you use, these are not lossless. They have some losses. So if your conversion state is less, your conversion losses will be less as well. But in dual stage, since conversion stages are more, your losses will be more as well. Right? So what you want is control over how you are implementing this whole inverter logic. So what you have is you want your solar PV panels to be operated at MPPT. So what is MPPT? It's the maximum power point tracking. So what is this maximum power point tracking? It's this point at which maximum power is available. Uh, uh, sorry, this point at which maximum power is available for your from your solar PVs, and this comes in this in the current and uh, voltage that are usually observed at this MPPT point is less than your open circuit voltage or short circuit current. So how you do is you use an MPPT control algorithm. So you give the output of your solar PV, which is the voltage and the current, to this control algorithm, and it gives you a reference DC link voltage. This DC link voltage is then fed into another controller, where the controller controls the DC link voltage to be at the reference value only, which then issues a reference D-axis current, which is used to issue pulses for our system. Since we want a reactive power control of our from our inverter, what we usually do is with the AC current control, we also provide a reactive power control, where we give a reference reactive power. So usually we want voltage regulation or reactive power management, and using this control logic, we can provide this management by issuing a reference Q at our own volition. This then issues the PWM pulses required to control your inverter, and the output of which is fed back to this is fed back to this control algorithm, and the output voltage is then issued with a phase lock loop. This phase lock loop synchronizes the output with grid voltage magnitude and frequency. So you want and phase angle, sorry. So since what you're doing is you're connecting your PV panel directly to the grid, right? So you would want a perfect synchronization, and this synchronization is implemented using this phase lock loop. This PLL uh, gives you this phase angle, which is used to control which is used to issue these PWM pulses, which is then controlled by the inverter. So this whole controller logic, it's very, this is very um, uh, I mean, it's a very wide, big control algorithm as per se, right? You would see that you have an MPPT algorithm, you then have a DC link voltage control algorithm, and after that you have your power and AC control current control algorithm, which then issues the PWM pulses. So all of this is required to be able to connect your PV to the grid, because at the end of the day, the PV the solar irradiance is very intermittent, and your output from your PV would also be intermittent, and you would want since you would want to extract maximum power out of your PV panel to reach maximum comfort. It's generally this control algorithm is derived up to be able to provide that level only. So all of this is used to control your PV converter. So in the demonstration, we give the three-phase AC voltages and AC current and the DC voltage and current to the analog input port of the Opal RT. I don't have the diagram for Opal RT, but similarly, this analog input or output card and this digital input or output card is used to give these is used to so now this inverter is like following grid following. So normally I read as grid following inverters are current controlled. Why it is so? Because of ID star. So grid following, yes, because you would want to follow the grid conditions. So it's what you're doing is you are trying to mimic the output of your PV circuit to be able to mimic how the grid conditions are looking. So it's usually what it's doing is it's controlling this it's issuing this ID star to control the output of your inverter by issuing accordingly the PWM converter. So it's a grid following algorithm. Why it is so? Why are grid following inverters are current controlled? So let me put it this way. So let's say that okay, so just a second. So why are grid forming converters current controlled? So I don't have a perfect explanation for this question, but as far as I can tell, um, the the DC link voltage control that we provide, it's usually used to output the DC link in such a way that your maximum for power point tracking is there. So usually your MPPT, you run your controller at MPPT only when it's connected to the grid. You don't want it to run at MPPT because following the maximum power could be difficult because the irradiance could switch its values very quickly. So the Pmax can be very high at a certain second, and the next second it can be very low as well. So the DC link voltage that the MPPT algorithm gives the output, it gives this DC link voltage, which is able to uh, give you this. Just a second. It's able to give you this current for your whole, uh, which is able to give the current that is able to provide how this PWM, how this inverter would behave. So let's say that your whole system it's behaving very erratically. So the best way to be able to provide control is by mimicking how the power is fluctuating. If you use voltage, this voltage is also behaving very erratically, right? That's why your DC link reference is changing, and your DC link reference is being used to control this DC link capacitor's voltage accordingly. So the control algorithms give you the current to follow so that your DC or AC current inverter's output is also mimicking the AC currents or the AC currents required from your output algorithm. But why only ID star is used in following grid following inverters? I don't have a perfect explanation. But yes, it's due to ID star only because this ID star is what is being taken out from the control algorithm, which is controlling how your DC link voltage is behaving. So that is how your AC current control is being implemented for your solar PV inverter. But why only ID star? There's no rational explanation that I can come up with it as of now. So mm, yeah. So where was I? Yes. So the whole of this analog input port, what it does is it takes in the input of this AC currents and AC voltages, and as well as the DC voltage and current. And it gives, and the control loop is implemented in RT Lab, which is implemented through MATLAB or Simulink. This RT Lab is nothing but a wrapper for Opal RT for MATLAB or Simulink platform, and this gives you the PW, the output of which is fed into the digital out, is taken out from the digital output port as in the form of PWM pulses, which are used to control your inverter. So a dual stage convert inverter is something very similar. It's used to implement control for both of these converters. Both of the converters, which are which are the boosting stage as well as the inversion stage. You can see MPPT, since you have first the boost converter and then your inverter, you first implement the control logic for your boost converter, which is then used to give the DC link reference, which is the DC link reference to be able to mimic the to be able to provide pulses for the DC-AC conversion stage. So all of this they implemented in real time at the at the Opal RT section and were able to uh, provide you with how the demonstration in real time would look like. So this is what is so this is what was for the solar inverter demonstration. So any questions up until now? Any doubts? Okay, in grid forming, same inverter acts as voltage controlled inverters and it acts as current. Normally, best PCs are act as both. So that's why. Yes, but yes, but why it's done is because So as far as I can think is, if you're if you're if you're control following the grid, you should be able to uh, since your uh, this PWM pulses are coming from your DC link voltage control stage. So it's beneficial if you use the current control algorithms, because your voltage could fluctuate if it's not perfectly in loop with the voltage should be in perfectly synced with your AC grid voltage side. But in falling stage, since there is no a forming stage, there is no AC grid, your voltage should be in voltage control state, because you don't have a you can't mimic your AC side, because you don't have an AC side altogether. And your BESS, which is your energy storage, they then act as they are then used to mimic the grid conditions, because they can supply power which is not dependent on the conditions prevailing based on the weather or anything else. But normally, this why this current controlled and not voltage controlled, I feel it's because of this only, but I don't have a perfect explanation as of now. I'm sorry for this. Yeah, I'm also learning. So okay, so if there are no other doubts, we'll move forward. So yeah. So next we did was what we wanted to do was how DFIG is how DFIG control is implemented for wind turbines. So let's first of all discuss what is the power conversion stage for wind power generation. Just a second. Write your question so that I can answer it, so that when I upload. So watch out for this space in when I upload this lecture on YouTube. You would be if I could find a perfect explanation for that. So a wind power generator, what it does is it converts, as its name suggests, the wind's kinetic energy to electrical energy, right? And through what way? So your wind's kinetic energy is it impacts on the wind turbine, which then is connected to a gearbox. So what gearbox does is, if your wind is hitting it at a very slow pace, it tries to make sure that the speed of rotation is fast enough. That's what your gearbox does. And this gearbox is then connected to your generator, which is generally an induction generator. Uh, there is a reason for that. I'll explain that as well, which is connected to a prime mover. And this prime mover is nothing but it's connected to the gearbox, which is rotating the rotor inside that induction generator. Then it's connected to a power conversion stage, which is optional, which is then converted from transformer and then connected to the grid. So this provides isolation. If something goes wrong here, it should not go to this power grid side, right? So this transformer ensures that this isolation is there. Now, what is a DFIG? So a DFIG is nothing but it's an evolved form of your traditional induction generator. So traditionally, your induction generator, it is only a single supply, right? You extract power from your stator. But here you can extract power as well as deliver power to your rotor as well. So it's a double input, a dual input, dual energy input kind of a thing. So it has this dual energy input. So uh, so why it's done is, it's because usually wind speeds could be synchronous at synchronous level. So it can be at 50 hertz frequency. It can make your rotor stator produce currents at 50 hertz frequency. It can be super synchronous. It can be fast enough, more than your 50 hertz frequency. or subsynchronous lower than your 50 hertz frequency to produce currents at 50 hertz, less than 50 hertz frequency. So using this DFIG, we use this back-to-back converter, back converter, which is nothing but an AC DC AC converter. So this is used to this is a kind of a converter which is used to enable two-way power flow to and from stator and rotor. And this is only possible. This DFIG generator is only possible in the slip ring form or wound rotor form, because only then you have the access to your multi-phase bindings or your multi-phase slip rings. So So the main modification from a single phase generator is nothing but the addition of this AC-DC AC converter. And this helps because what we want is we want variable speed drive, right? So this variable speed drive, which is dependent on your speed of your wind, uh, it should be able to produce output at a constant. It should be able to produce the output power at a output at a constant frequency. So we let's talk about what is RSC, what is GSC. Hmm. RSC is your rotor side converter. So as its name suggests, it's connected to your rotor side, and it's responsible for adjusting the current rotor currents frequency and magnitude. Just looking at this chat. Okay. Hmm. So it's used to control your rotor, because at the end of the day, how your rotor is behaving at low speed and high wind speed is what it what tells you how it should behave in the first place, right? So why this we want is we want the output of the stator to be at a constant frequency, and it doesn't matter how your wind speed is behaving. And this this rotor side converter provides control, which is given as it increases the rotor speed. So I'll explain every detail, but I'm just giving you a brief overview. Increases the rotor speed when wind speeds are low. Okay, so I'm taking an example from a lecture online. So what he said was, let's say you are running a football field, right? You have a football field. This is a football field. And let's say you are powerful enough, you can control how this football field could rotate. Okay. Let's say your coach asks you to run at 2 RPM, or let's say 8 RPM, but it's only possible for you to run at 2 RPM. So what you do is you run at 2 RPM, but you make your this football field run at 6 RPM. And what happens is, from the point of view of your coach, you appear to be running at 8 RPM only. So it's exactly how this control is provided from your rotor side converter. So when it's running at a low speed, it makes your rotor run fast, and when your wind is at very high speed, so I should mention low wind speed. Then low wind speed, it decreases the rotor speed when high wind speeds, because all you want from your wind generation is not to control the power. I mean, you are in a way controlling the power output, but what you're controlling more is your frequency of operation. You want your frequency to be perfectly balanced. So this is how your torque speed. So this is your sync speed. In this place, it's working as a generation. So this is your top slip characteristic for your induction generator, right? And here it is working as a motor. Now, what you want is you want to be able to run your rotor in this region so that it is able to produce power. Now, all you want is this power output from your generator, and your DFIG does just that. It helps you adjust your speed in accordance to your speed variability. As your wind speeds are varying, you can adjust your speed variability with respect to that. Moreover, it helps you regulate reactive power as well. Why? As you know, to establish this rotating magnetic field in your induction generator, you know that you utilize some form of your reactive power. Now, using this analogy, using this how you're controlling your rotor magnetic field, you can regulate the reactive power as well. So all you're doing is you are controlling how your rotating magnetic field is moving. If you want your rotor to move fast, you can just make sure that the hypothetical electromagnet, which is producing this rotating magnetic field from your stator, you can help it produce at a faster rate so that if your rotor is moving at a lower speed, this electromagnet would move at a higher speed. And in thus, you can control the generation from your your frequency from your DFIG. So this happens in this way. Let's say your prime mover is working like this. So I've taken all of this from a YouTube lecture funded by National Science Foundation USA. So like for example, we have Anusandhan National Science Foundation of Serb. They have this National Science Foundation over there. So it's from Jim Pytel. You can watch it at your if you want to watch, but I would be explaining it as well. So so this is how your output should look like. So let's assume that your stator is producing a constant power output, right? Since this is what your stator is doing. At synchronous speed, you are injecting some power from how your wind speed is. Let's say your wind speed is helping your prime mover rotate at a synchronous speed. This then helps produce uh, some stator power, which is constant. The rotor power then required to maintain the synchronous speed the requirement is less. So which is being fed back to the rotor circuit. This power is less. Let's say you are at a hypersynchronous speed. What is a hypersynchronous speed? It's synchronous speeds less than your synchronous speeds. The power injected, the wind power that is being injected to your prime mover, it is less, right? Since the mechanical power is less, let's say this field, the rotor power needed would be more. So your rotor is taking power from the output of your stator. If it's at a constant speed, the stator power taken would be more. And since this is more, the total power output would be less. Since you are taking some part of that power out to control how your rotor is behaving at a hyposynchronous speed because you want to maintain that synchronous frequency. In the hypersynchronous speed, your prime mover is behaving very fast. It's injecting a lot of power. So you are working in this stage, let's say this stage. So the input to your rotor is minimal, zero, and your synchron stator, since it's at a constant speed, your total power injected back to the grid is very high, and this hypersynchronous speed is used to make sure this is not zero, this is very less. I mean, this is not drawn to scale. So this is very less, and what your power is giving back to the grid is very more. Let's say you are at a very high hyper synchronous speed, a speed which is very high. So the power input to your prime mover is very high since stator power is same. Now, since you already have a lot of power in your rotor side, what your rotor side converter is doing, it is feeding this power back to your stator side. So it's taking some of this power, feeding it back from this AC back to back converter, which makes sure that the power that your wind generation is outputting is very high. So in this way, your DFIG, by using its AC back-to-back converter, which is a bidirectional converter, uses the bidirectional power flow to inject power if it's running at a very high speed, take power if it's running at a very low speed. So this is how a DFIG converter usually behaves. Any question? Any doubts? Clear. I would request if someone is interested, they can follow this person, Jim Python. He is a member of NSF, and he can tell you why how this whole thing works. So you will be able to better follow if you are not following this lecture. But I hope you are following. I mean, there's no point in discussing anything, right? Next, we moved on to the demonstration of VMS. So again, let me give you a disclaimer. It is impossible for me to provide a demonstration because I don't have access to the resources that the instructor was having. So just take it as a session that where I tell you, I revisit the topics that were covered earlier, and we'll discuss if you have questions or not. So then we moved on to how battery management system. We studied the demonstration of a battery management system. Now, what is a BMS? BMS is used to, as its name suggests, manage the battery. Why do you want to manage the battery? There are few examples as well. In India, you must have seen that EVs catch fire very easily, right? Recently, Tata Nexon was very infamous for that. Two or three cars caught fire very quickly in a hot and humid weather. So this is usually because of the hot and humid weather that is prevailing in our country. The BMS, which is being taken from countries which are outside of the of Indian subcontinent, the BMS algorithms that we are employing are not completely relevant to us. So this BMS is not able to maintain the battery temperature in a certain way so as to suit the temperatures of our Indian subcontinent. So a BMS does the exact same thing. It monitors current, voltages, and temperature. So you are monitoring current, voltages, and temperature, and then estimates the SOC or SOH using online estimation techniques, which is usually Kalman filtering techniques. So, and after that, they use cell module balancing. So, what is cell module balancing? So, all of your battery packs have individual cells. Let's say we are using lithium ion battery. So, they have individual lithium ion cells. So, each of these cells, their open circuit voltage is a function of the state of charge as well as the temperature, right? Now what happens is usually due to manufacturing variations, or let's say operating conditions, or other stuff, you may have such a condition that there are different voltages or SOCs for cells in the same pack. Now due to this, what happens is the estimation of SOC or SOH is erroneous because the data that you have uh, is wrong in the first place. So so what we usually do is in the battery management system we have cell balancing algorithms employed. These cell balancing algorithms usually are passive or active. In passive, uh, yes. In passive we dissipate extra energy. That is, we use a resistor, a shunt resistor as shown. We use a resistor to dissipate this extra energy so that all of the cells could have equal uh, uh, energy. So, but this is a lossy way, right? But this is something that is being employed widely. But there are active methods as well, where what we do is if a cell which has a higher SOC or higher energy, we provide some part of that energy to other cells. So this can be cell to cell. or we can bypass entirely. We can use a capacitor to um, store that amount of energy for a certain time, so that all of the cells could have equal uh, energy. Or we can use pack-to-pack cell balancing method as well. So let's say you have multi-pack. So usually a battery energy storage, you would have multiple battery packs, and you can have active balancing methods for that battery pack as well. So under the cell to cell, we can use adjacent cell to cell. Let's say an adjacent. So as its name suggests, we just use a neighboring cell to submit power to the neighboring cells, or we can use any cell to any cell, or direct cell to capacitor or any other thing, right? So these are some cell balancing methods. So as the name suggests, so this is a sorry, this is a passive balancing method. What you do is you control these switches to so you connect these switches when you observe that your batteries have individual cells have irregular amount of energy stored. So once you are familiar with that, what you do is you dissipate this energy into these shunt resistors, and this dissipates the extra energy, and uh, what you are left with is equal cell balancing at all cells. And this is an active balancing method where your battery is controlled using this switch to store energy to this capacitor. So what you can do is you can store this energy to this capacitor, and let's say your capacitor store energy increases, and your neighboring cell has lesser energy. You can then supply this energy to this cell using this single pole double throw switch. So this is called a single pole double throw switch. It has a single pole, that means it has a single arm which is connected to two different terminals. It can be connected to different terminals. So this is an active balancing method. There are other active balancing methods as well, but such as the buck boost method, or flyback converter method, or Chuk converter method as well is there. And there is this I forgot its name, resonant converter balancing methods as well. So you can look for it. I've discussed some of these methods in my week 3 lecture as well. I won't be going into detail. So the instructor then talked about, uh, he showed the demonstration for a passive balancer, which is an integrated circuit available readily in the market, which is used to balance the active, which is used to balance the cells and dissipate an extra energy through the resistors present in that IC. Then the instructor moved on to the electric vehicle. So uh, right now, as you can see, there are different ways of. I forgot asking any questions up until this slide. Thumbs up or a thumbs down or a question. I can then move ahead. Sir, in inverters. Yes, in inverters, what? Yes, tell me. So I have other topics to cover as well. So it's not the end of the class. So uh, the inverter question that you asked, I'll definitely follow up with you. But as far as what as I told you, all I can think of is that the DC link voltage provides this reference current, which can be used to provide control over your AC currents. In videos I've seen DC to AC, they mentioned DC voltage is 1.414 times of grid peak. Okay. Yes.
Hello.
Yes. Yes, I can
My
hear you.
voice is clearly audible.
Yeah.
In details, I feel like they mention to act as an inverter to convert DC to AC. There will be one condition such that we have to maintain DC voltage as greater than root 2 times of peak of the grid voltage.
Okay.
But in SunGrow inverter, in one of the data sheets, I feel like even though we are not meeting that condition, that inverter is like in inverter data sheet I seen.
So I didn't follow your exact question. So you're saying that you mentioned the fact that the DC link voltage is generally considered to be 1.414 times of grid peak or root 2 times grid peak, root 2 VM.
Uh,
But I couldn't follow after that. What you were asking in a data sheet, what did
it
you see?
is in data sheet they said like 800 volts is the AC voltage
Okay.
and DC voltage 860 to 1500.
Okay.
Where we are not meeting that condition. 860 volts DC, 800 volts AC.
Oh, so you're saying 860 is something that we are not. This 800 that you saw, is it VM that you're talking about, the maximum voltage?
It is the RMS voltage.
It's the RMS voltage. So your grid peak would be root 2. So you saw root 2 VM because generally root 2 times VRMS is something VM. So it should be greater than VM, I suppose. It shouldn't be greater than root 2 VM.
A peak voltage means root 2 times of VM only. Na? Like
Yeah,
in the
yeah. No,
video, in the
VM, no. Wait. VM is your peak voltage. VRMS is under root two, VRMS is VM upon root 2. So the peak voltage is under root 2 times VRMS. So it's no, what you
yeah,
have written is root 2 times of grid peak. So you should write root 2 times of grid RMS.
2 times.
Okay, root 2 times of grid RMS. Whatever, it should be greater than grid peak. So what you're saying 800 volt over there is RMS.
Yes.
Okay, so I don't know what data sheet you were looking at, but so can you tell me the data sheet? I can open.
Yeah, I
Hmm.
SunGrow inverter.
Sun, can you write in comment section so that I can
Yeah.
just hmm. I'm waiting for you to write that in the comment section.
Actually,
Oh, you're trying to find. Okay. I'll wait.
uh, I am trying to share that.
Okay, you're sharing the picture. Just let me see. Maximum. Okay, 800 volts. This is RMS only. 680 to 880. Okay, put your DC link. Hmm. So, Dharani, what I've generally heard is, or what I've generally seen is that uh, the rule of thumb is that it should the Okay, sun grow solar. That will no. The rule of the thumb is that the it's not just the the DC link voltage generally should be greater than the peak. That's what I've heard. But here the peak is not it's not something that hmm, I don't know why it's written like this in this inverter. So do you have any other data sheet for any other PV inverter we can check?
Huh. Yeah, this is a solar inverter, sir. In best TCS, that condition is valid. Like now we are following the best TCS. In that we are maintaining like AC voltage as 690 and battery voltage in the range of 1100 to 1500. There
So
I'm
okay,
observing
okay,
this
okay,
condition.
okay, 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 okay. So just a second. 680 times 1.41. It's still 960. So what I feel is the the voltage range for your nominal power it's given as 860 volt to 13. So what are you considering for your experimentation? What are you doing?
Sir, like in the project, we are connecting 29 solar panels that are like in the range of we are meeting solar voltage also depends on temperature, na, sir. We can't say, but the 29 modules will meet something 1200 volts. But sometimes it may come to 1000 volts also DC.
Okay, so but Harini, so usually what we do is we generally have it the DC link voltage is generally kept greater than peak voltage only, and it's usually done because of efficiency issues only. But why? So I don't know from where you got this. Okay, so from where you got this data sheet, I don't have an explanation of why it's not. But if you're keeping it around, what is the one root two times 800? It's around
It,
1131, right? So if you're keeping
uh,
it around 1200, are you getting um uh, good results?
yeah, sir. With the 1200, we will get good result, but that depends on temperature also. Now, sometimes that
Yeah.
voltage may go to 1000. When we checked the string voltage for
Hmm.
inverters, there are conditions that it goes to 1090 also.
Hmm.
But at that time, the inverter is operating only. It is generating power also.
Yeah, if you are keeping your DC link voltage at a higher level than your inverter, it would generate power. But uh, I I don't know why it's written like this in your data sheet. But if you are getting good results, if you're keeping it at 1200, it shouldn't be a problem as such. But it depends on temperature, as you're saying. But yeah. So
Maybe like that is a two-stage inverter also, sir. Maybe that there will be DC to DC boost converter may increase the
uh,
voltage to get V max.
this
I don't know
the
inside what
sorry,
the operation.
I forgot asking. Is it it's a single stage converter, right? What you're showing me?
I don't know, sir. In this concept, not only I learned there are two types of inverter, single stage and double stage like this.
Oh, so you usually have this double stage for boosting your output power, right? But
Yeah.
yeah, let me check this sun grow, right? So,
In now what I'm doing in the project, best projects in features, now in the data sheets I seen it is maintaining that condition.
mhm. So see,
But
it's the condition is always there. Your DC link voltage has to be greater than your this
root two times of
the
it.
peak voltage because of the fact that your real power should flow from DC link to your inverter, right? If you want to maintain this flow of power, the DC link should have to have a higher voltage reference than your peak grid voltage. But But yes, I mean, in this data sheet, what I feel is they have given a range of values, right? That it can the voltage, this voltage can be supported by your DC link or whatever your uh, this output is, and
Because
what the AC voltage.
in
Mm, the
because
yeah,
in solar plants normally depends on area of the land. Sometimes there is a
yes.
chance to connect only less series modules there, like 28, 29. So there will
Mm-hmm.
be some range for the inverter operation.
Yeah. So it's better to it's always a better thing to give a range of values so that you know that at what
Mm.
values your output would be produced, or what your output would be better in your the whole range. But if there are doubts related to, let's say, your grid frequency, but what I feel is what they have given is the output AC, right? The normal grid, the nominal grid voltage, is something that they have not given. So what they have given is
Uh,
that your inverter could support from this range to this range for your DC, and for your nominal AC output, it can support from your uh, who is saying?
yes.
So for your nominal AC output, it supports this voltage range. So they have given you a voltage range for you to check at which level you want to produce output. Because there are many conditions your DC, the solar panel depends. It can be temperature, which is of course how your solar is irradiating and stuff like that. So uh, uh, but the practice generally is to keep your DC link voltage at a voltage level which is higher than your grid voltage or your peak grid voltage. That's because you want the real power to flow from your DC link side to your inverter. And that would only be possible if your DC link is at a higher voltage level, right? So that's the main reason for that to do.
Okay, sir. But one small doubt, like DC power flow because of voltage difference, but AC power will not flow because of voltage difference now.
Yes, but the see what you're doing is you are trying to mimic your grid output reference, right? So whatever your grid output reference is, your real power. It's now I'm not talking about how your uh, how your inverter is behaving. The DC, the solar is producing output at a DC rate, right? It's a real power that it's
Yeah.
producing. So you want this real power to flow from a high reference voltage point to a lower reference voltage point. That is how you are maintaining your DC link voltage to be. Now, this could only be possible if you measure how your, so since you are already using the output of your converter, which is your VAC and IAC, to lock it to the phase of your grid frequency, right? So what the V voltage is doing is it's locking itself to the grid voltage magnitude and four phase angle. But how your ID current behaves, this ID star, it will only flow if it's flowing from your DC, the higher reference to a lower reference, right? So this ID star
Yeah.
reference gives the PWM voltage frequency to be able to match that voltage level. So that is how the whole converter operation is forming itself. So these are multiple control algorithms linked to each other. Only possible for real power to flow from that side to this side is by creating this
Hmm.
reference voltage to be at a higher level than your nominal voltage.
Got it, sir.
Okay.
Thank you.
Hmm. Okay, so where was I? Yes, so we are done with this battery management system. Then we moved on to electric vehicles, demonstration of, yeah, no worries. So then we moved on to demonstration of electric vehicles. So there they used an electric vehicle charging replica, right? So first I will tell you what are the different ways of charging your EV. So you have an onboard charger only if you want to convert your, it's only there for lower power uh, operation. So let's say you have AC voltage, it's generally available at home from 2 to 7.4 kilowatt. Or if you are at a, let's say at an industry, at a commercial establishment, it can be as high as 22 kilowatt as well. So there you can use at homes, we have available mode 1 and mode 2 chargers. This is used, so normally at your home you have, this. plug point. So you can directly plug in your EV, and it is connected to this EV-AC onboard to pass this energy, convert this energy from AC to DC, and pass it down to the battery. This mode 3 is for higher power levels, mostly after 15 kilowatts to 22 kilowatts. This is because as your power level increases, the protection devices or the converters or the controllers, the size of these also increase. So it's to keep the size of this in your battery support onboard charger minimal, you generally move to the off-board chargers. So mode 3 is an off-board charger, and it's connected to your grid. So all of these are used only for the AC side EV supplying equipment. But let's say you have DC chargers. So this DC chargers, you can have the fastest available chargers or DC chargers only. These can go from 2 kilowatt to 200 kilowatt, which is a very higher power. And they are available in three types, which is CHAdeMO, which is usually used in USA and Japan. Then you have Combo 2 and Type 2. So in Combo 2, you have both, right? You have the 2-pin chargers as well as your normal um, a Type 2 charger as well. So this is how this charger looks. And the DCs are generally available only in mode 4, which is off-board charging equipment, because they can be at a very higher power level. They can be used to supply at a very higher power level. Now let's talk about residential EV charging systems, right? So let's say you have an EV. What you do is you will use it to travel to your working place. You would then come back. So you would have used certain amount of your battery, and what you will do is you would immediately charge it at your home. Let's say you reside at a colony where all of you are working people, and what you do is you all have EVs available at your home. You use it to commute to your work, come back to your home, and then connect it to a charger. Now, what you're doing is you are trying to withdraw electricity, which is generally uncoordinated, because a distribution system operator cannot control, because all of this is behind the meter. In the residential way, this is all behind the meter resources. The DSO doesn't know what is happening behind the meter, because you're connecting your EV to the power socket available at your home. Now, what happens is usually this creates a lot of imbalances uh, in the low voltage networks, which are generally available in the residential area. So I have used this image from a lecture from University of Melbourne, where they were explaining something about operating envelopes. I won't be talking about that as of now. It's by Louis Okua, Bassi, and Jingzhu. So what happens is usually, let's say that you have a head of feeder transformer, and it's connected to a LV network, which is a low voltage network, usually 230 volts AC, right? 230 volt, 50 hertz AC. Now, if you all have EVs available at your residential places, which is a low voltage network, what happens is when you connect it to your power socket, the voltage, since it's a function of the current that is being drawn at your premises, and this voltage usually tends to sag at the bottom of the feeder. As you can see, at the head of the feeder, the voltage is at its nominal level. As it approaches the last of the feeder, the voltage starts sagging. Why is that? The amount of current that uh, importing from your distribution transformer, it will increase as soon as you charge your EVs, right? Now, since this current is increasing, what is happening is the losses are also increasing in the system. If these losses increase, what happens is the voltage present at the last of the terminal or the last of the feeder, it falls. Now, if you are at the head of the feeder, let's say you are connected directly to the distribution transformer, you are at a win-win situation, because you won't experience that high loss. But what is the mistake of that person who is residing at the last of the feeder, right? It's not his responsibility to manage the network resources, but it's very difficult for a distribution system operator to manage a low voltage network. Why is that? Is because most of the generation, or most of the energy usage is behind the meter. It can't predict what is happening behind the meter. So it becomes useful for us to provide a coordinated control over this uncontrolled charging. So you want to control this charging. Now, how are you going to do it? Is through some of these methods. You can use time of use pricing. You can check who all can connect your chargers at what time. So time of use pricing would generally mean that you would tend to decrease the load consumption. You won't charge it as soon as you come home. You will charge it at the night when the load is minimal, right? Or you can use basic on or off. The DSO can control your distribution transformer to just uh, uh, to disconnect your power supply or something like that, which is not usually relevant, right? You can also use bidirectional controller where you can supply energy to the grid so that you have extra energy available by the distribution system operator to distribute across the feeder. You can have vehicle to home so that you can use the extra charge available from your batteries to charge your to use your home appliances, vehicle to building or vehicle to any other load. Or you can have dynamic pricing. So all of this can be used to provide a coordinated control over this charging. uh, Usually it's useful for residential charging because that's the kind of load somebody cannot predict. So in this lesson, what they were telling us is we can have an operating envelope for this import as well. So you can have a minimum and a maximum range for all of these houses based on what kind of PV or home appliances they are using. So I won't go into this detail, but this is some way where you can provide a coordinated control by providing an import range below under which only you can import power to your system. But then you would say, what is the equity? What's the mistake of this house connected to the last of the feeder? Why it is responsible for this voltage sag while all of the houses above it are also utilizing the power in the same way. Now, one more way to provide a coordinated control is by using transactive energy systems designed for the distribution system. I don't know if you all have heard this, but so let's say that a utility can issue demand response control, right? It can say, okay, I'll give you 250 rupees. Don't charge your EV right now. Charge it when it's 1 a.m. So you will say, okay, give me 250 rupees, I'll charge it. But what if it says, I'll give you 50 rupees? 50 rupees is nothing for you, right? You would say, no, I want to charge it as soon as I reach home. I want to charge it. So what the utility is doing, it's communicating only one way. It is broadcasting demand response prices to you. But why not you as a customer provide this price response back to this consumer? You act like, okay, I will switch off my charging, give me 100 rupees right now. So this bidirectional communication between your distribution system operator and your individual customers is something which is called transactive energy system design. So in this transactive energy systems design, you exchange something that is of value to you. It can be money, it can be power, that is something that you are valuing. So all of these ways is one way where you can control these uncoordinated resources, so that all of this voltage issues that your LV network would face eventually in the coming days is not there in the at the beginning. Right. So the instructor then moved on to discuss about the demonstration of the EV charging system, which is something beyond my lecture today. So is everything clear up until this point? Yes. Okay. Then the instructor moved on to AC/DC microgrids. So I've already discussed in depth about AC/DC microgrids when we were discussing about the control of these microgrids. But once again, I'll talk about them. So what are AC-DC microgrids? So these are hybrid microgrids which have both AC buses as well as DC buses, or AC loads as well as DC loads, or AC generation as well as DC generation, right? So, so let's say you have an AC coupled hybrid microgrid in which you have an AC bus, in which you have an AC bus, but with that you have DC generation as well as AC generation and DC loads as well as AC loads, right? So this is a kind of an AC coupled hybrid microgrid. The other kind of microgrid is your DC coupled microgrid, where you have a DC bus and you have your DC distribution generation, your AC distributed generation, as well as your DC and AC load, all connected using interlinking converters. But since your utility, which is AC, inherently AC, you need to have interfacing converters. These interfacing converters help you be in contact with your AC bus. Now, in a hybrid microgrid, you have both DC bus as well as AC bus, which has DC loads generations and AC loads and generations connected to both of the AC bus and DC bus. So these have interlinking converters, and as you can see, as you go on to uh, this expansion, you can see that the number of converters increase. So since the converters are increases, these converters are costlier in nature. So if your converters are increases, first your losses will increase because of higher conversion losses, and then your cost of the whole system will also increase, right? Now, all of these systems, you would have seen one thing is common, a storage element, right? All of these have a storage element. Now, I've already talked about why a storage element is important. So can anyone tell me why storage is important? So I've answered all your questions. Now it's time for you to answer my question. Why is storage required? And we can use, yes. So it's basically all of these microgrids you would have seen that these use distributed generation, which are generally renewable in nature. And all these renewable resources are having two things in common. One is intermittency. They are intermittent. Second, variability. They can vary any second. It can change from a few kilowatts to a few megawatts in certain seconds only, right? So a storage could be used to smoothen out these intermittencies that are available in this renewable resources. Second, let's say mm, you see a complete blackout and your DC your microgrid goes into an islanded mode of operation. Your storage elements will provide the reference voltages or the reference voltages that are used by your converter logics or your converters to be able to provide uh, the control algorithms with the reference voltages of your system. Third, they have excellent black start capability. Let's say you experience a complete shutdown of power. Your battery energy storage systems, they don't need a ramping facility. They don't need to ramp up. They can just strictly they have a very high ramping capability, and they can straight away start providing power, which is not possible in thermal generation, which take time to provide power when they go into a complete shutdown. So they have excellent black start capability. Now, there are two kinds of storages. One is a capacity oriented storages, and the other is access oriented. So I've talked about both of these kind of storages, but I feel I haven't differentiated both of them. So you use two kind of storages in tandem with your microgrids. One, you can use batteries in tandem with your supercapacitors. Now, why is that? Your batteries have high energy density. They can store a lot of power and they can deliver a lot of energy, but their power density, their the the speed at which they can provide this energy, the power, it's very low. So they usually don't have fast responses. So your batteries, your conventional batteries, are called capacity oriented because these don't have one fast response, but they can typically be used to store a lot of power for long term balancing. And they can be able to buffer out a low frequency oscillation in your DGs. So these are conventional batteries, your pump storage, and your hydrogen storage as well. Now, access-oriented batteries, these are for providing fast responses. So they can deliver power immediately. And these are generally used for short time disturbances. These are generally supercapacitors, flywheels, etc. Right? So these are the two kinds of energy storage available for your microgrid. Now, a microgrid also has two kind of management systems. So there is one power management. So I'm discussing these topics again, which we have already discussed in, I guess, week 8. No, week 7. So just follow along. Hmm. So, uh, so a power management strategy is usually used to provide voltage and frequency regulation because you want instantaneous control, voltage and frequency regulation, because you want instantaneous regulation or instantaneous because you want to make effect on the instantaneous operating conditions of your grid. So let's say your voltage is sagging, you want to provide um, uh, um, reactive power support immediately. So if you want to affect the changes in your operating conditions instantaneously, you have to use a power management strategy. Then you can have energy management strategy. In energy management strategy, you use it to provide an optimal production of power. So, so let's say you have a couple of batteries, right? So you want to maintain their SOC between 30 and 70, yet provide uh, energy to the critical loads. So what would you do? Power management or energy management? You will use energy management, right? Because you would formulate an energy management scheme which will be able to provide power to the critical loads as well as keep your SOCs of your individual. Yeah, any practical applications where it plays important role than best, because I think spinning reserve is the only thing where they ask more power in short time. Remaining all like RE smoothing, frequency regulations, all are best applications. So let's say the best battery energy storage always works in tandem with the supercapacitor. There's a reason why. They are low power density devices. So even though they can store a large amount of energy, the rate at which they can provide this energy is low. So let's say your system goes into certain sudden, uh, what should I say? The real power is suddenly collapsing, right? So the so you can start operating your best. They can start changing their real time power generation accordingly. But your supercapacitors can pitch in. They have low energy density. They don't store a lot of energy, but they have high power density. They can quickly provide power to the system. So when there is a very short disturbance for a very short period of time, which you have to provide immediate relief to, you use supercapacitors to provide power immediately. Now, BESS has its regulation. You can't just simply use it to provide power immediately, right? So As you see, the chargers you have, the maximum that I've seen is 400 or 460 kilowatt for charging. I'm sorry, the maximum coupling that I've seen. But this supercapacitor can provide immediate energy insertion to the grid as soon as you see the disturbance happening. Although they can't provide power for a longer period of time, they can be used to smoothen out certain disturbances which are not which the batteries are incapable of. The frequency regulation or the smoothing, although are done by BESS, but the shorter disturbances which are there for a very the transients in the system, I should say, the transients in the system can only be supplied by the supercapacitors, not by the BESS. You can check. I mean, if you already you know how to read a data sheet, right? You can check the power density for a supercapacitor and a power density for a battery energy storage system, and you will be able to feel that if there is a sudden transient, which one would be able to, which is better able to help that transient. So that is something that you can check on your own. Okay. So yeah, sure. So let's move ahead. So we've already discussed these power management schemes for AC/DC coupled hybrid microgrid. If you have doubts, I would request you to please follow the week 8 lecture. I won't go into detail as of now because I discussed this in the same um what you see what you say the same thing over there only. So these are power management strategies, but there are energy management strategies as well, and these can be of different types. So one is decent. I don't know why I have this empty page. Okay, so yeah, these energy management schemes are generally differentiated based on what kind of communication network they are using, and second, what are the access to local variables or the global variables, right? So let's say you have a microgrid which has a physical connection with all of the DGs with provided with local controllers. So LC means local controllers, DG means distributed generation. So in decentralized method, you don't need any communication network. That's right. So you don't require communication. So you don't really require communication. So what you do is you use here group controls. So the group controls are used here. For DC microgrid, the group control is between P and V. And for AC microgrid, the group control is between P and F. And in a decentralized method, all of the individual uh, components are controlled based on the group control laws available for that. So, yes. Anything else? Okay. So, in a centralized method, all of your individual DGs which are connected to each other have communicate with each other. So, all of them. Okay. So, I don't know why I mentioned group control over here. So, in decentralized, you don't have group control methods. Individual control laws govern. So the individual controllers of the local controllers govern the control of the distributed generation. So these are not at all reliable methods. So these are not reliable at all, right? In the centralized method, there is a need of communication network. So now, as although the communication network is there, you would also need a central operator because they will be in direct contact with each other. They won't be in direct contact with each other, but the contact would be managed by a central node. So the CC is the central controller. And if there is a single point failure, if there is a problem at a single local controller or a DG, it could affect all of the other DGs as well, because since all of the control or all of the energy management strategy is being controlled through a central operator which is in contact with all of these DGs. Third, since we are using a central controller, we have access to global variables. So what do you mean by global variables? So let's say you have an AC bus and you are trying to synchronize it with it. So the V and F of that AC bus is your global variable, and your individual V and F for each of these DGs could be different, which are being used by which are being managed using the the interfacing converters with the coupled bus. Next, you can have distributed communication where your individual DGs are directly in contact with each other. So communication network is also needed here. Second, since communication is needed, this is generally called peer-to-peer, P2P communication, right? So here, since each of them are in touch with each other, if a single point goes into failure, the whole network won't go into instability, that's for sure. Now, in your centralized method, group laws govern your control algorithms because your central controller has V and F available readily with him, and he can use them to provide control to all of the other DGs. So let's see. So let's say you have a hybrid AC-DC microgrid, and you have a DC side, you have an AC side. So in DC side, as I've told, you use PV group law, and in AC side there is PF group law. So what you do is you convert V and V and F in per units, and the steady state point, if each of these per units, what you are doing is you are enforcing that in per unit both of these values should be equal. So the interlinking converter which is in contact with each other, this interlinking converter oh, sorry this interlinking converter is enforcing that the per unit voltage of your DC microgrid side and your per unit frequency of your DC microgrid side, the values of both of them should be equal. That is how a centralized control is governed over the whole system. So this is what the instructor talked about for this week's lecture. That's all I've covered. So let me give you a brief overview. So I started with why validation is required. I used this PPT by Dr. Shreyasi Som, which is a senior who has received a degree, PhD degree. And I told you how software in loop validation is done, how controller hardware in loop validation is done, and then how power hardware in loop validation is done. And at the end of all of these validation lies the field validation state. So today we discussed demonstration, and we revisited our concepts of demonstration of these solar inverters. We discussed single state solar inverter and how it's implemented. I'm yet to get back at this question by Dharani, why ID star for grid following. But I generally feel that since the voltage is the output of this voltage is being used to stabilize, synchronize with the grid, the controller must use the AC currents to be able to figure out what is the control required. But I'll still get back to it. Now, then we discussed wind power demonstration. Demonstration, we discussed what is the wind power generation, how DFIG is used, and then I went on to explain what is the various control coordinates or operation coordinates of this wind DFIG. Then we moved on to BMS, how cell balancing methods are there. Then we moved on to EVs. We discussed what are the various problems with the residential EV charging. Then we discussed AC/DC microgrid. So any questions up until now? Then we'll move on to questions. Any questions? Okay, since there are no questions, I'll move to questions. So, what is the function of gate driver circuits in an inverter? So, a gate driver circuit, it's used to provide PWM pulses to your switches and isolate the circuitry. Now, since you use a control circuit board to provide these pulses, you want to make sure that if there is an instantaneous, or if there is a uh, 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 what you say, if there is, let's say, a transient that can affect my control circuitry, I want it to be isolated from that. So let's say I use some control logic and it is flawed, and my power circuit is like it trips. So this inrush current that it would experience, I want it not to be given back to my control circuitry so that I could provide control over that. So it is used to isolate that control circuitry from the power circuit. So the answer is both A and B. Identify the correct statement. PI controller is used to regulate the current in synchronous reference frame. PR controller is used to regulate the current in stationary reference frame. PI or PR controller can be used irrespective of the reference frames. Yes, so this is true. So this PI controller is nothing but a proportional integral controller, and it is used to provide the regulating current in the synchronous reference frame. And PR controller, which is a proportional resonant controller, it's used to regulate the current in stationary reference frame. Now, this is something that I would ask you to go back to your control systems book to check why it's used, but the answer is both A and B. Third, DFIG is capable of rotating at. I have discussed in detail today. So can anyone tell me? Who can tell me the answer for it? Hmm. So why is DFIG used? So it's used as a variable speed drive, right? So I want my uh, system to be able to uh, provide power irrespective of how the wind power is, right? How the wind is moving. So it can be used at synchronous speed. It can be used at subsynchronous. A. Is it A? So I discussed here, right? So there are different modes of operation. You can have synchronous, you can have subsynchronous or hyposynchronous, or you can have super synchronous control as well. So the correct answer is that DFIG can rotate at all kinds of speed so that it is able to match the wind speed if and when it requires power. So the answer is all of the above. Next, DFIG is what type of machine? So we want access to rotor windings, and in which kind of induction machine is the access to rotor windings available? Slip ring. Yes. So the answer is slip ring. Okay. Number of cells connected in series provide what? I don't think it provides higher current capacity. So if I have a cell connected in series, each of them have 35 volts, let's say. So what is VAB? It's the addition of all of them, right? So it can provide higher voltage. Yes, series increase voltage and parallel increase current. Great. Identify the incorrect statement with respect to different types of storage elements. So we discussed today, right? What is the incorrect statement? Come on, who can tell me? Okay, so let's talk about the third um, statement. In a microgrid, we cannot use two. Yes, the answer is A. So let's talk about it. So let's leave out A. Let's talk about B. Response time of supercapacitors is fast compared to lithium-ion batteries, right? So this is a true statement. In a microgrid, we cannot use two storage elements such as lead-acid battery and a supercapacitor together. Hmm. Such as a lead acid battery. So yes, this is also true. Lead acid battery has a higher power density, and we want a higher energy density with a higher power density, not too high power density storage elements. So all are incorrect, can't be our option. And supercapacitors can be used for cranking of diesel generator used for power backup. This is wrong because the diesel generator works altogether in a different what do you say uh, operation, right? It provides AC power for immediate backup, but supercapacitors can be used to immediately charge it because the diesel generators work on prime mover connected to a generator, right? So it depends on how fast your pistons are moving and how fast the pistons move the prime mover. So supercapacitors can't be used for cranking of diesel generator. So the Power Grid has demonstrated the smart grid technology capabilities in collaboration with various solution providers at which location. So let's leave out this. The answer that I've been given from NPTEL 7th, right? Okay, it's Puducherry. So you can see what kind of operation they have done. Which of the following is not the smart grid R&D area in the field of ICT and cyber security? Who can tell me the answer for this? So find areas which are suitable for yeah, maybe D. Yes, D, because all of the other things are suitable for ICT and cyber security field area, but ancillary services of converters, it's not something that is applicable for ICT and yes, yes. What is the need for energy management in microgrid? What is the need? Yes. So we want to manage the renewables, batteries, and loads. We want to reduce the stress on the grid during peak hour. We want to obtain energy balance in an islanded operation. So the answer is all of the above. So charging of the batteries is preferred during which of these modes as mentioned below? Yes. So we want to charge it at an off-peak hour because if they are charged at a yes, if we want to charge them at an at a peak hour, it will increase the overload of the transformer, which is something that we don't want. 11th, which of the following is a false statement with respect to the power flow control strategy adopted for managing the energy of the DC microgrid? So, a power flow control strategy is something that is able to determine the operating modes of all the units based on factors like wind power generation, the demand, battery, SOC level, and etc. So, it's used to check, yeah, smooth. Okay, okay, I'll talk about it. So, it's used to tell us how, yes, I'll I'll tell. Wait. So it's used to tell how the optimal power flow should be for all of these units to maintain such that the wind power generation, if it's varying, the load demand, it also varies. The battery has to see what is the level of it, and the if the grid is connected or not. So if we want to manage the energy of the DC microgrid, a peak demand reduction is a false statement because power flow control strategy can't. Yeah, the answer is C. It can't manage the peak demand reduction because it derives the how the energy should be allocated to different generations and load available. Yes, the answer is C. So, which of the following is feasible during peak hour mode in a grid connected DC microgrid? No answers. Okay, so when it's peak hour, the load is maximum, right? So if the load is maximum in a grid connected DC microgrid, okay, if a load is maximum, what we want to do is we want to absorb as much as power from the grid. This is wrong. So, A, let me tell you. So, a grid which is since you are connected to the grid, you can't ask for uh, as much power as you want because then the grid which is connected to other systems as well, it won't be able to allocate that much amount of power for you. So what you would do is you would increase the generation from all of your renewable generation resources. So let's say you have solar PV, you will start operating it at MPPT so that all of your peak hour demand could be met from your localized generation, and then you can ask power from your grid because asking power from your grid costs you money as well. So you're importing power, right? As a microgrid controller, would you want to import power at a higher rate? No. So what you would do is you would first inject maximum available power to the grid so that if there is other load connected to the grid, you would be able to provide power as much as possible to the grid, not increase the debt over the grid as well. You don't want to integrate power more loads, and you want to operate renewable sources in power dispatch mode. No, all of your renewables uh, will be uh, uh, will be at MPPT. That is, they are not dispatchable. Whatever power they are producing, all of them is being injected to the grid so that the peak hour mode can be utilized, so that all the generation available is utilized for your peak hour. So, any questions? I thought peak hour mode means grid having more power. No, no, no. Peak hour means load is maximum. I told you, no, load here. Load is maximum. Every time when you said off peak hours here, where was it? Off peak hour here. Huh. Charging of batteries at off peak hour. Why did you do it here? Because load is less, right? So you can charge more. When you charge batteries, your batteries appear as load. So by charging it off peak hour, you are making sure that your load is not at a maximum level. Yeah, got it. Great. Next question. In the islanded operation of DC microgrid, suppose the battery reaches its lowest SOC limit. Which of the following action is preferable? So you are not connected to the grid. Um your battery is now at its lowest level. That means renewable generation that you are having, it's not at, yeah. So what you want to do is you want to make sure that your non-emergency loads are turned off so that all of the available power can be supplied to your critical loads. So this is very easy, right? Full form of SCADA. Anyone can tell. Yeah, supervisory control and data acquisition. Last question. And we have more, but which of the following case of islanded operation of DC microgrid where the battery is completely charged and the source power exceeds demand, which of the following control is operated? Yeah. So your battery is fully charged and you have more power than the demand. So What will you do? Will you shut down your system? Yes. You would operate your PV at off MPPT. You don't want it to provide more power to the load because the load is already less. Since the generation is already there, you don't want to increase your generation even further. It would cause your frequency to go high. Which one is correct in MPPT mode of cell? So this is very easy, right? Quickly. C. Is it C, Dharini? Okay, let's see. This diagram. Now quickly tell what is the answer. VOC is greater than VMP and ISC is greater than IMP, right? So the correct answer would be VOC is greater than VMP and the answer is not there. So the options look incorrect. So VMP is less than VOC and IMP is less than ISC. How can it be C? VOC? Oh, yes. Yes, yes, yes. The answer is C. Yes, you are right. I'm sorry. Yes, the answer is C. Next, what is the purpose of PLL in solar inverter control? Yes, tracking grid voltage magnitude and phase angle. So it wants to track. Okay. Hmm. Next, DFIG is a. This I've already asked. It's slip ring. Yeah, someone wants to
So,
ask something. Mm-hmm.
PLL is used for the synchronization of voltage and phase. Frequency is some frequency synchronization by.
Okay, so if your see, so if your phase angle of your voltage is matched with the grid voltage phase angle, your frequency will always be matched. Why? I'll leave it to you to think over it how phase angle and frequency are linked. I've explained this concept when we discussed about, I feel when we were discussing about PMU's operation, but you can check. Yeah. No, 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 not real power. No. So when your phase angle, so already the class has extended to a certain time, but you can check my week 3 or week 4 lecture where I was discussing PMU phasor measurements, voltage and frequency. There I've discussed about it. So fourth, a private entity has taken a contract from government to establish a hybrid microgrid that should continuously operate in grid connected mode. Which of the following convention of the microgrid is economical as well as efficient? So in DC, you require converters. AC/DC, you also require converters. So since converters increase conversion losses and converters are expensive, you will use AC coupled microgrids. Yeah. AC coupled, na? You want maximum efficiency as well as you want it to be economical. So you want your price to be low. Yes. Select the correct statement. Internal resistance is a temporary reason for cell imbalances. This you can check with sir's lecture. I'll just give you what the answer is. So it's temporary reason. No, it's a permanent reason. If an internal resistance is altered, yes, all are incorrect. This is also wrong. I should, no. Number of cells connected in parallel provide, as said by Dharini, high current carrying capacity. Seventh, IEC 62840 standard type is related to this. You can check, it's battery swapping. It tells you, so battery swapping concept is that you come to a swapping station, you swap your batteries from what is available over there. So the communication infrastructure or the standard over there is set up on IEC 62840. The terminal voltage of a battery decreases with dash while being charged. You can answer this question. Okay, so OCV is a function of SOC and temperature. Yes, all of the above is the correct answer. Ninth, interlinking converters works on the principle of equalizing what? Last question. Just a second. Okay, so increasing temperature increases voltage. No, I'm just saying it's a function of temperature. So the terminal voltage of a battery, it decreases when the temperature increases because of the chemical composition of the battery. So when the battery, and you can check now, the terminal voltage of a battery decreases with increasing temperature. Hmm. Because the chemical composition changes. Yes, equalizing DC side PU voltage with AC side PU frequency. Last, BMS monitors the value of each cell. What? Yes, all of the above. So, so we discussed all of the questions. That's very good, and we covered everything. So, any doubts while I disconnect this meeting? Okay, if I have time, tell me. So I have to catch a train at 10 p.m. I'm just telling you. Uh, yeah, tell me. Short circuit ratio versus 10. Um, okay, so okay, so huh, okay. I'll tell, but if you don't understand something, we can continue next time as well. But I'll just talk about it. So a short circuit ratio is nothing but 1 upon X, right? The impedance of the resistance is generally neglected since we are using R is very, very less than X. So it's 1 upon X, which is the reactance of the system. Now let's say what happens is usually the the short circuit ratio. So it's ISC by IR, right? 1 upon X. Now, if the impedance of the system is more, what would happen? So if the impedance of the system is more, the short circuit X by R. X by R. Are you sure? It's 1 upon X, na? Let me check. I can also be wrong sometimes. Yes, it's 1 upon X only. So you can check uh, whenever you get time. So what usually happens is as the impedance increases, right? So what happens? The value of X will increase. So your short circuit ratio will be less. Now what happens is usually if the impedance of the system will be more, so the short circuit current will be less, right? So the system, even when it gets, let's say, some fault happens in the system, if so, what happens? The relay work on the principle of measuring this short circuit current. If the short circuit current is low, how will the relay measure it? Right? So the sensitivity of the relay will decrease because the impedance is more of the system. So that's why what usually happens is if the short circuit ratio is less, that means impedance is more, the relays won't be able to detect if a fault has taken place or not. That means the strength of the system will decrease. So in order to measure the strength of the system, the impedance should be less, and the that's why we say now 1 upon x r by x ratio, it should be less for a system, so that the sensitivity to the short circuit current wouldn't be there, and the short circuit current would be more, so that if a fault occurs, it is detected by the system as quickly as possible. So that is what SCR means. So I have just discussed a very, do you have idea min what it should be? Idea min? Can you tell me what is idea min? Minimum value. So I don't have a minimum value what should be maintained. It depends on system to system, but yeah, it's something for you to check. I mean, you can see online in some papers where they have mentioned about the strength of grid, where they would have mentioned how. And one more thing, so it's not just the short circuit ratio, it's also that if the impedance is more, the voltage regulation that is there in the system will also be less. So let's say that the since the impedance is more, the drop in the voltage would also be more, right? So there are multiple reasons as to why the short circuit ratio, which is 1 upon x, should be as high as possible. But the minimum value, I don't have a. So generally, for synchronous based systems and integrated to the system, the ISC should be at least 5 times the rated current, right? So you can see what could be the best alternative for you. Yeah. Okay. So I have one question to get back to Dharini regarding that, but uh, I hope that you are able to gauge something out of this class today. I mean, um, it extended very much, but I wish you all the very best for your next week, and wish you a very happy Holi as well. I would like to bring this session to a close. So I would request all of you to please leave this meeting. Yeah, happy Holi to you as well. Yeah. So Dharini, if you are no, she left, right? Okay. Okay then. I request you to please leave.